Today we are very happy to invite Xin from Sydney to come to give us this talk about tensor network-based decision diagram. Xin received his bachelor degree from University of Wuhan in 2019, and then he moved to University of Technology Sydney now. So this work is done there, and his current interests include quantum simulation and circuit verification. So let's welcome him.
Okay. Thank you. Thank you very much for letting me here to introduce this work to you. And in this work, we propose a tensor decision diagram that can be used to represent quantum circuits, and it can be used to do simulation and verification of quantum circuits. And basic ideas of this decision diagram comes from using binary decision diagrams to do simulation and verification of classical circuits. And also, we have used a lot of techniques that have been used in quantum multi-value decision diagram. Okay, then this is a binary decision diagram, and you can say a classical circuit can be represented by a Boolean function, and you can say this binary decision diagram is just to represent this Boolean function. From here, you can see that you can see this dotted line as a logical and then certain line as logical and then you can translate this binary decision diagram as x2 plus x1 and x3 and x4, and then you can say this is exactly represent this Boolean function. And you can see that compared with we represented as a truth table, we take 16 values. If you can represent it as this binary decision diagram, it can be really compact, and then this representation is also unique, and then it can be used to do a lot of things, especially equal checking and a lot of verification tasks. And then following, I will introduce basic ideas of tensors. A tensor is a multi-dimensional linear map, and you can say this graph, you can see this as rank 1. Here we use node to represent tensor, and we use edge to represent. We create the egg of this tensor, and the number of eggs are the rank. And you can see this is the rank 1 tensor, and this is rank 2 tensor, and this is rank 3. And normally a rank 1 tensor represents a vector, and the rank 2 tensor represents a matrix. And then this, if the rank is bigger than 2, it can be represented a multi-dimensional array. And then a lot of tensors can be connected to form a tensor network. And here you can see that these are 2 tensors, and they are connected with this edge, and these are also 2 tensors, and they are connected with 2 edges. And then the most basic concept of tensor network is the construction, and they should be, that is, 2 tensors should be summed up with shared index. And then you can see these 2 tensors can be constructed to a single tensor, and these 2 tensors can also be constructed to form a single tensor. And if these 2 tensors are all rank 2, and then it is exactly the same as the matrix multiplication. And you can see that here we use Z to represent the Pauli Z matrix. Okay, Pauli Z matrix. And then you can see the construction of these 2 tensors should be in the summation over Y of these 2 tensors. And then you can say here, if you for this constructed tensor, if you take X and Z as 0, that is 0, 0 will be equals to phi 0, 0 times psi 0, 0, and then plus phi 0, 1 times psi 0, 1, 0. And then you can say if x they are all 0, then y must if y takes value 1, then it should be 0. Then so then this summation should have only one item that is not 0. Then this should be psi 0, 0 should be equals to 1 times 1, and is exactly 1. And then finally you can see that these two tensors are constructed from identity matrix. And then this is the constructing of tensors. And then you can see that in quantum computing, where a quantum state can be represented, a single qubit can be represented as rank 2, can be represented as a two-dimensional vector, and then it can be also seen as a rank 1 tensor. And here, an qubit state can be represented as a rank 1 tensor, but here we take that every index in this tensor takes value 0 and 1. Then it can also be seen as rank n tensor. Then for this tensor, you should apply an index here, and then for example x 0 to x minus 1. Then for this tensor, phi 0, 0, 0 should be exactly in this value alpha 0, and phi 0, 0, 0 and 1 should be exactly in the value of alpha 1. And then for quantum gates, for single qubit gate, it can be seen as a rank 2 tensor, and for two qubit gate, it can be seen as a rank 4 tensor, and for n qubit gate, it can be seen as a rank 2 n tensor. Here, you can say for this tensor, if you represent it as phi x y, then phi 0, 0 should be this value 0, and phi 0, 1 should be this value 1, and phi 1, 0 should be this value 1, and phi 1, 1 should be this value 0. Then you can see that all these quantum states and quantum gates can be represented as tensors, and especially in this quantum circuit can be represented as a tensor network. Certainly here you can use different index, but here we use concept of hyperedge, and we use one index here. We use Wallace index x0. Since that if these two index take different value, then since T gate is diagonal matrix, and if these two index takes different value, and then this tensor, especially this tensor network, must be in value 0. So we can here use yeah.
Is there any internet problem, or your cell phone is not working so well?
Oh, so my network is not very stable.
I mean, it sometimes disconnect. I mean, the voice did not continue smoothly sometimes.
Oh, okay. I will try to close my VPN, but I don't know if this Microsoft Teams can be used. So can you still see my screen now?
Yes, I saw your.
Yeah, I think
I see your screen now.
Yeah. I think this time maybe better since that I have closed my VPN.
Okay.
Okay. So I will continue. Yeah. So we use tensor networks to do a lot of things in quantum computing.
Sorry,
comes from the basic idea that quantum circuit can be seen as a tensor network. And this is also the basic idea of our we use the tensor descent diagram to do a lot of things in quantum computing. Okay. Okay. Following, I will start introducing tensor descent diagram. Before that, I should give you the Bo-Xiang expansion of the tensor.
Sorry.
Yeah, you can see that.
Yeah. Do you still open some other app?
Sorry,
I'm not sure. Now the voice is okay, but previous is well, it's not working well.
Oh, okay.
I think continue. Sorry.
Yeah.
Okay.
I don't know if not something wrong with my network. I think that it's always not stable.
Okay, we just continue. Thank you.
Okay. I will try to speak slowly, and if you have any questions, please stop me. Okay. Okay, I will introduce the Bo-Xiang expansion of a tensor. And for a tensor, you can see that if it depends on a lot of index, and then you can take an index out, and then it can be divided into two parts. And it can be written as x times phi x equals 1 plus x prime times phi x equals 0. Here we think that this index x takes value 0 and 1. So here, if x takes 1, then x prime takes 0, and if x takes 0, then x prime takes 1. So here you can see that here you can see that for this Ponizit matrix, and if it is the rank 2 tensor, and which is equal to this matrix, and if you set x equals 0, and then it will be corresponding to this column vector, and then you can see that phi x equals 0 will be exactly this vector, and also phi x equals 1 will be exactly this vector. And then you can see that if x takes value 0, and then this part should be 0, and then this part should be phi x equals 0, and then finally phi will be equals to this vector. Here you take x equals 0. So if y is still 0, then it must be 1, and if y is 1, then it must be 0, and it equals to this vector. So you can say a tensor can be decomposed using this Bo-Xiang expansion. Okay, so according to this expansion, we can construct our tensor descent diagram. Here you can, for a tensor which depends on a lot of index, including x, then you can use a node labeled with the index x and two successors to represent this two sub tensors. Here we use 39 to represent the 0 subtensor phi x equals 0, and use 39 to represent the 1 successor phi x equals 1. Also, it may be seen more clearly from this example. Here, we also consider this circuit as a rank 3 tensor. So here, it is a rank 4 tensor, but we use these two index. We use the same index in these two next. So we can use only 3 index here. And for this tensor, we have this is value here. And if x 0, y 0, y 3 takes value 0, 0, 0, and then this vector should take value 1. Here you can see that from this graph, you can see that x 0 takes value 0, and then y 0 takes value 0, and then y 3 takes value 0, and then this tensor is 1. And similarly, if x 0 takes 0, y 0 takes 0, y 3 takes 1, then this vector, and then this tensor should be 0. And it is similar for other values. Here you can see that when x 0 is 1, y 0 is 1, y 3 is 1, and then this tensor should be minus that. From this circuit, you can see that if x 0 takes 0, and then this will not be applied, and these two gate will take value 1. So now will be no phase here. And here, since that sinusoid are not being applied, so next to Hammer gate has been merged to identity matrix. So you can see here Y0 and Y3 is exactly in identity matrix. You can see that Y0 is takes value 0, Y3 takes value 0 is take value 1, and when Y0, Y3 takes value 1, 1, and then it takes value 1, and for unvalues it takes 0, and then let's represent on identity matrix. And similarly, when X0 takes 1, then there will be a phase I here from these two tickets, and then this signal will be applied, and then Y0 and Y3 will be H, X, H, which equals to the point zeta matrix. And then you can see here, it's exactly I times point zeta matrix. You say here when Y0 takes value 0, Y3 takes value 0 is I, and Y0 takes value 1, Y3 takes value 1 is minus I. And then if you take this I out, and then you can see that the matrix formed from Y0 and Y3 are exactly the point zeta matrix. And you can see that this graph really captures all the vectors or all the values of this tensor. And also, this is not compact. You can see that we can run compact in binary descent diagram. But here we just represented as this fully expanded descent diagram, and now is no any compression here. And then we should take a lot of techniques to make it compact and make it unique. First we will use a technique called normalization, and this is a way to and this is part of the technique to make it unique. Here we first take the values. We put the values of the tensor in the original tensor descent diagram. We put the values in terminal node of this descent diagram, and then we will put the values of the tensor to the weights of the edges. We do this since that if you put these weights on the edges, then you can see that if these two subtensors differ only by a factor. For example, if here is I, and then these two subtensors should be differ only by a factor I. So if it's this case, and then if you take the weight to the width of the edges, then these two subtensors can be merged. So we will take this. We will put this the values of tensor to the width of the edges. And then yeah.
I just want to check, is the node representing the matrix, the final matrix element in the sequential product, or it represents the weight, right?
Yeah. Here for this graph, the value of the tensor should be obtained through the multiplication of the corresponding weights, the water weights along the path. Here, for example, in this graph, when X0 takes the value 0 and Y0 takes 0, Y3 takes 0, and then the value of this tensor along 0, 0, 0 should be this weight times this weight and times this weight. Here for this, it should be 1 times 1 times minus I and equals this minus I. And this is similar for other passes. Here also this 0 should be tensor. Also, when later you will see that we will not use this terminal 0 node, so it will not confuse. Yeah, but for other cases, you should take one value along the path to obtain the value of the tensor. Yeah.
Okay.
And then when you put the value of the tensor to the weight of the descent diagram, then I think that there are many ways to do these things. For example, you can multiply here by 2 and divide it here by 2. And then so you can really have a lot of ways to do these things to represent it as a tensor. So we should have a lot of restrict to this weight. Here we take next, and you can see that for every node there's 2 weights, and you can set the weight that has a big norm to 1. And then, for example, here this is I, and this is minus I, and they have the same weight and they have the same norm, and then you should set this to 1, and then this should divided by I, and then this should multiply by I. And here you can see that this I and minus I should turn into 1, minus 1, and I. Okay, I think this is the basic operation of this normalization procedure. And it's similar for other node and for every node. Okay, this is 0, so it will not be considered. And if this is not 0, and if this is not 1, this should be set to 1. If this is A and A not A is not 1 and A is not 0, and then this should be set to 1, and this should be set to A. And for this weight, if this is 1 and this is 0 and this is A, it should be similarly to set this to 1 and set this to A. And similarly, one way should be moved upward until we reach such a case which is a unique representation. Okay. And then we should do something to make it compact. Since that here you represent out this form and it is not compact at all. The basic idea of this procedure is called reduction, and here that is to merge all the nodes that represent the same tensor. First, we should merge all the terminal nodes to one terminal node that is labeled with this integer 1. And so you can see that this graph should be merged, should be changed to this graph. And one terminal nodes are merged to 1, and then terminal node 0 should be this 0 should be put as should be seen as the weight of this corresponding edges. Okay, and then it can be further merged, can be further reduced, and you can see that here for these two nodes they represent the same tensor. It can be seen as a rank 1 tensor phi y3, and phi 0 equals 1, and phi 1 equals 0. So these two nodes represent the same tensor, and then they can be merged. And also these two nodes, can be merged to this one, and then also these two nodes can be merged to this one. So finally, this graph can be reduced to such a graph, and you can see here that this graph is really compact compared to normal and so on. And it exactly captures all values of this tensor. For example, you can see that when x0 takes 0 and then y0 y3 should form identity matrix. It is exactly the identity matrix. You can see that y0 takes value 0 and then y3 takes value 0, and then it equals to 1, and y0 takes value 1 and y3 takes value 1, it equals to 1, and y0 takes value 0 and y3 takes value 1, and then it should be 0. Okay, and that is 1 times 0, that is 0, and it's similar for this part. Okay, I think this is a reduced tensor diagram, and we also call it a tensor diagram since that we do not we do not take it as two different things. We just we call all of them as tensor diagram. But you can see that this is really compact, and in fact, it's the most compact one. It has this is not to represent the same tensor. Okay, Okay. Following, I will start to introduce the operations of tensor descent diagram. Since that for this small circuit or giving you a small tensor, you can easily represent it as a tensor descent diagram. However, if I give you a big circuit, how can you represent it as a tensor descent diagram? So you need to operate between different tensor descent diagrams. Here, what I mean is that if I give you a big quantum circuit, you can easily construct the tensor descent diagram of every single quantum gate. And then you can use the operations of the tensor descent diagram to finally construct the tensor descent diagram of the whole circuit. And then there are mainly two operations of the tensor descent diagram. First is the addition. For example, for two tensors, here you know that for Xin Hong expansion, phi can be divided into x times phi x equals 1 plus x prime times phi x equals 0. That it can be represented as this in TDD can be represented as this form load labeled with x, and the two successors represent phi x equals 0 and phi x equals 1. And then similarly, psi can be represented psi equals to x times psi x equals 1 plus x prime times psi x equals 0. And then it can be represented as this graph node labeled with x, and the two successors representing psi x equals 0 and psi x equals 1. And then the addition of these two tensors can be represented as this form: x times phi x equals 1 plus psi x equals to 1 plus x prime times phi x equals to 0 plus psi x equals 0. And then you can see that here it can also be represented as node labeled with an index x, and two successors representing phi x equals 0 plus x equals 0 and phi x equals x equals to 1 plus psi x equals to 1. And then you can see that for two TDD, the addition of two tensor descent diagram is exactly remain as node labeled with index x, and do the addition of these two sub TDD. Okay, you can see that for this TDD, phi x equals to 0 can exactly be represented as a sub TDD 2. So from this graph, you can see that phi plus psi will be a node labeled with x, with two successors representing phi x equals 0 plus psi x equals 0. This is exactly this sub TDD plus this sub TDD. So you can see that the addition of two tensor descent diagram can be executed in such a recursive way. So if you want to do the addition of these two tensor descent diagram, you should you only need to do the addition of these two 0 successors and the addition of these two 1 successors, and then they should be connected to a node labeled with index x, and corresponding results should be used as the corresponding 0 successor and 1 successor. And then another operation of the tensor descent diagram is the construction. It should be divided into two cases. First, if x is an index that should not be summed, here you can see that, for example, x should be remain here, and the summation is on y. So you can see that here you can see it as in this case. Here you phi is a tensor that depends on index x, and psi is a tensor that do not depend on x. And then the construction of these two tensor should be a node labeled with index x, and with two successors representing phi x equals 0 here we use this symbol to represent the construction here. So this is the construction of psi x equals 0 and construction of psi x equals 0. And from this Foreshadowing extension, you can also see that the construction of phi and psi should be x times, and the construction of phi x equals 1 and psi x equals 1. Plus x prime times phi x equals 0, the construction of x equals to 0 and psi x equals to 0. And from this graph, it's just node neighbor with index and then doing the construction of these two zero successors. Here you can see that psi x equals, since that psi is not dependent on x, so psi x equals 0 is exactly similar to psi, and this is also similar to psi. So this should be the construction of phi x equals 0 and psi. This is similar. It's not psi is not dependent on x. And then another case in that x is an index that should be summed, and then so you can see that in a result, the index x is not already null. So this should not be a node neighbor with index x. So you can see that for these cases, the construction of phi and psi should be here. You can see that the construction of phi and psi should be in the summation of the construction of phi x equals 1 and then psi x equals 1. And the construction of phi x equals 0 and psi x equals 0. So from the graph, you can see that the construction of these two tensor descent diagram is exactly that first you do the construction of these two zero successors, and then you do the construction of these two one successors, and then the two results should be added, and then so you can say this should be the final result that represents the construction of these two tensors. Okay. And then with these two operations, addition and constructing, and then so here, if I give you a big quantum circuit, you can represent every single quantum gate as a tensor descent diagram. It can be easily done, and then all these tensors can be constructed, and then the result should be in the tensor descent diagram of the whole quantum circuit. And then if you can obtain the tensor descent diagram of the whole quantum circuit, and then you can do a lot of things. Okay, and these are some applications of the tensor descent diagram. The tensor descent diagram can be used to do the simulation of quantum circuits and do the equivalence checking of quantum circuits. And it can be used to compute the trace of a quantum circuit, and can be used to do the verification and all those things. Here is an theorem. You can see that this representation is unique. That is for two that is if two tensor descent diagrams represent the same tensor with the same next order, and then this tensor descent diagram should be isomorphic. And you can see that for this circuit and this circuit, and now tensor descent diagram are all at this form. So you can see that these two circuits are equivalent. Here you can see that these two T gates can be merged to this S gate, and this two Hartmann gates and the central gate can be merged to this control point zeta matrix. So you can see that these two circuits are exactly equivalent, and from this tensor descent diagram, you can see that they will have the same tensor descent diagram. And since that you know that if two tensor descent diagrams represent the same tensor, and then they should be isomorphic, and then from this fact that if these two circuits have the same tensor distance diagram, and then you can you can know that these two circuits must be equivalent. And we also now also some other examples, and when we calculate the tensor distance diagram of this quantum circuit in a common use benchmark, and we can see that this tensor distance diagram is as this form. It exactly represents identity matrix. So you can know that this circuit is which corresponds QFT10 is exactly not QFT10. It's running equals to the identity matrix. And also you can use it to calculate the trace of quantum circuit. And for matrix, the trace of this matrix can be calculated by constructing this tensor network. That is to collect the input and the output of this matrix. And for quantum circuit, that is to collect the input and output of every qubit. And then constructing this tensor network, you can obtain a trace of this quantum circuit. Here, when using tensor distance diagram, you can first represent every quantum gate as tensor distance diagram, and then you can talk Wallace tensor distance diagram, and finally you can obtain a trace of this quantum circuit. Okay. The advantages of using tensor distance diagram is that first, it is compact. Since you can see that a lot of nodes in the tensor distance diagram can be merged, so it can use less memory spaces. And then if you use the tensor distance diagram, you can cope with the quantum circuits with much larger number of qubits. And also this representation is unique. A tensor will have only one tensor distance diagram representation if you given a fixed index order. And also it can be very easily to be incorporated with other tensor network techniques. And for example, slicing and other circuit partitioning and a lot of other you can use more flexible construction order and other techniques. And here are some here are some experiments we have collected on the tensor distance diagram. Here is reference data for using TDD reference quantum circuits, and this is the time for using quantum multivariate distance diagram to reference the quantum circuits, and this is the time for using TDD, and this to using TDD with some circuit partition schemes, and this is using tensor network. You use the Google tensor network packages. You can see that in most of the cases, at present, TDD is not as fast as the quantum multivariate distance diagram. But if you combine it with some circuit partition schemes, it can be faster. And when combined with the Google tensor package, you can see that if the number of qubits is bigger than 15, then it should be out of memory. But it will never out of memory for quantum multivariate distance diagram and tensor distance diagram. Also, you can see that although at this time tensor distance diagram is not as fast as quantum multivariate distance diagram, but you should notice that our TGD package is using Python language, but this quantum multivariate distance diagram is constructed using C++ programming language. So I think that this can also show the efficiency of our tensor distance diagram. And also we have a lot of tasks that TDD can outperform quantum advanced disintegration. For example, if we calculate the trace of a quantum circuit, then TDD should work better since that it is just equivalent to construct a tensor network. But for quantum multi-value disintegration, you should first construct the quantum QMDD of the whole circuit, and then you calculate the trace of this quantum multi-value disintegration. But for TDD, you need not to construct the tensor disintegration of the whole circuit. You can just construct the corresponding tensor network, so it can be can work better. Okay. So in conclusion, TDD has the advantages of both disintegrams and tensor networks. It is memory saving, and the representation is unique, and it can be fractionally operated. And in future, we should I think we should give a more easily used tensor disintegration package that can be used for people who are not very familiar with this tensor disintegration. They can maybe have the basic concept of tensors, and then they can use the tensor disintegration package to do the corresponding tensor network tasks. And we should find more applications for tensor disintegration. Okay. I think that this is all my report. So please say if you have any questions.
Okay, thank you for your talk.
Yeah, okay, thank you.
Is there any question or comment from the audience? Maybe I will miss one point from your last two slides. What's the table? The big number represent the different number of representation you can represent, or what's the number meaning in the right hand side? What's the table? Can you the number is the time you need to construct them, or is the representative power?
Oh, sorry, I don't get your question.
So what's the QFT for different type of representation? What's the number in the right hand column?
Okay. Here, this column represents the number of qubits, and this column represents the number of gates in this circuit. And this is the time for quantum value disintegration to construct. And this is time for construct the quantum value disintegration of the whole circuit. And this is the corresponding the largest number of nodes appeared in the process of constructing the quantum value disintegration. And this is the final node of this the corresponding quantum value disintegration. And this is the time for constructing the tensor disintegration for the corresponding circuit. And then this is the corresponding nodes, the biggest number of nodes and the final number of nodes. And this are time and biggest number of nodes when we use TDD combined with some circuit patching schemes. And this is using TDD combined with another circuit patching schemes. And this is time for using Google Tensor Network to represent represent this corresponding circuit.
Okay. Okay, thank you. Yeah, my colleague has some questions. Wait.
Yeah.
Recently, China announced they use Tensor Network to beat the supremacy, Google quantum supremacy. How about your work and the Tensor Network ways difference?
I think for now, for network, they just for this for now tasks if you want to simulate a random quantum circuit, and you should find a better construction order and slicing schemes. And I think networks are just to using a big machine and aimed for a specific circuit, and then they find a better construction order, a better slicing scheme, and then using their machine, they can simulate the corresponding circuit in a relatively short time. Okay, but for my for my tensor distance diagram, it just for tensor distance diagram, it's just to represent a circuit in a relatively compact way, and also it can be operated easily. So these are two different things, but I think that they can be combined, since that the basic operations of tensor network can be done on using the operations of tensor distance diagram. You know that we can do addition and construction of two tensor distance diagrams. So you can also use tensor distance diagram to do nail tasks. You can they represent and then you can represent the corresponding tensors they use to you can represent the corresponding tensor they use the tensor distance diagram, and you can use the tensor distance diagram to do the same construction, and then you can also obtain the simulation result of a random quantum circuit. In fact, in my laptop, we can simulate a random quantum circuit up to I think 100 qubits and in a few seconds. But we just calculate a single amplification. Yeah.
All right, thank you. And I have another question.
Yeah.
Does the tensor network decision diagram and the tensor network construction two ways is easy to transport each other?
Sorry, using a tensor distance diagram and tensor network. What? I didn't get your.
Is the two representation is easy to transport each other? I want to use the tensor network decision diagram, and I want to transport a lot of ways, like tensor network, like China 2 or cool quantum or others. Is the easy? Or is
you say, yeah, you using that transform tensor matrix representation to a tensor distance diagram representation. A matrix multi-dimensional array to a tensor distance diagram. You mean that?
Yeah.
From a matrix, maybe a matrix to a tensor distance diagram. Yeah, I think it's easy. It's very easy. In fact, I didn't give the generation procedure. You can see that. I can give you this example. Here you can see that. For example, if phi is a big matrix and you want to transform it to a tensor distance diagram, first you can see that you use a node neighbor index X, and you should construct these two sub tensor distance diagrams. For this sub tensor distance diagram, it just represents the left part of this matrix, and for this sub tensor distance diagrams, it just represents the right part of the matrix. Okay, so for every sub with for every sub tensor distance diagram, it can, for example, be divided into two parts. That is the up part and the down part. So so using two index, it can be divided to four parts. And then, for example, if this is just a 2x2 matrix, and then you use that node, maybe I can. I don't know if I can write something. Okay, maybe this one I can. Yeah, I can give you a next example. For example, here you want to transform this matrix to a tensor distance diagram. Oh, sorry. Maybe. Okay. Oh, it's really. Okay. For example, here you should have a node labeled x with index x. Then you should further divided this subtensor to a sub tensor distance diagram, and then you can see that here it can be referred to this case. Okay. And then similarly for this part, you can represent that this one. So what I mean here is that this procedure can be executed in a recursive way. So if you want to construct the tensor distance diagram of this, maybe a bigger matrix, you just need to construct the tensor distance diagram of a relatively small tensor. This one, and for this one, it is exactly equivalent to construct two smaller tensor, and then when you reach a single value 1, and you get this node, so you finish this procedure. And in fact, I have the corresponding function in our TDD package, so you can use that to construct the tensor distance diagram of corresponding matrix. So you should not worry about that, I think. Yeah.
Okay, thank you. Is there any other people want to answer?
Okay, thank you. My question is, this tensor network seems like a very useful compact representation. So it's a tool can be applied in several different places. So is there any constraint of this method, or how's its comparison with other method representation, for example?
You mean what representation?
No, not represent. Maybe other method, or is there any constraint for this method?
You say the constraint of this method?
Yes.
I think that tensor distance diagram is one problem is that it is not always compact. You know, there are a lot of cases that it cannot be compact. For example, for this quantum Fourier transform for this case, you can see that the number of nodes grows exponentially with the number of qubits here. Also, this is to represent the whole matrix. If you do the simulation, it should be grows linearly to the number of qubits. But if you want to construct the tensor diagram of the whole circuit, the number of nodes grows exponentially. So it will take the corresponding memory spaces will grow sequentially, and the corresponding time grows exponentially. So I think that so tensor diagram cannot be applied to every cases. It should be it should be works for I think special circuits. If it for example if it's fast, then I think it will be compact. But for circuit like this quantum Fourier transform, and if you want to construct the whole the tensor diagram of the whole circuit, I think it will not work very well. But you can see that it is better than Google Tensor Network package, since that if you represent it as a matrix, and every time the number of elements of the matrix should be 4 times that of the first one. But here you can see that the number of nodes is 2 times of the first one. So you can using TDD you can calculate the corresponding diagram up to 22 qubits and within 1 hour. But you using a Google Tensor Network package that is to represent it as a simple matrix, then you can only cope with the number of qubits up to 14. Yeah.
I see. And is there any advantage of TDD over like BDD, binary decision diagram?
I think like if you don't need if you do not mean binary decision diagram used used for the I think National Taiwan University. If you not mean in that paper, normally I think that tensor decision diagram can be applied to more different places than binary decision diagram. It is because that binary decision diagram is designed for a Boolean function. And although in that paper, binary decision diagram is being used to cope with this quantum circuit cases, but this is not a commonly used method. This is just a special case. And normally, tensor decision diagram can be used to cope with all tensor network cases. So it can be, I think it can be used in a more flexible way and used in more different cases. Although in that paper, I think the bit matching paper, that one, the binary decision diagram are being used to cope with the quantum circuits, and it can be more efficient. But you also notice that the complex number that can be coped using narrow way should be should be a certain form. Not all complex number can be represented using a binary decision diagram now method. Yeah. Okay.
I see. Okay, thank you. Is there any further question? Okay. I think that's all. And thank you for your very nice talk. Thank you.
Okay. Thank you.
Oh.